Hello, good evening, everyone. So this is tutorial session 10 for the NPTEL course on various in calculus and its applications in control theory and nanomechanics. I'm Jaya Krishna Avatar, PhD student at the Department of Aerospace Engineering in the Ministry of Science, Bangalore. So this week we'll be reviewing the contents of lecture of week 11 of the course, which is Introduction to Nanomechanics, following the same template that we have been doing so far for all the drill sessions. We'll start with a brief review of some of the concepts, such as hypergeometric functions, nanomechanics in this course, or I would call it in a general sense, it's more of functions, advanced functions that we are going to cover in this week. I'll just call it as, instead of hypergeometric function, let me call it as special functions. Special functions, one of which is hypergeometric functions, and a bit of nanomechanics. So let's first review the special functions part. Special functions. Okay. At first, let me begin with the gamma functions. Okay. Gamma functions. So the gamma function is defined as the gamma of an argument z is equal to 0 to infinity, t to the power z minus 1, e to the power minus t dt. So t here is the running variable and z is our argument for the function. Now the some of the properties of gamma functions are, I'll just note down. Properties are that gamma 1 is equal to 1 and gamma z plus 1, and z here is a real number, uh, is equal to z into gamma of z. So this we'll be using this to identify during our course. And if say for say 4, z is an element of positive integer, then gamma of z is equal to z minus 1. I'm sure this is the when our argument happens to be a positive integer, then we use the traditional factorial. Okay, and then let's I'll be just reviewing hypergeometric functions, because I'll be discussing only those functions that we'll be needing to solve some of the problems in this lecture. The other is hypergeometric functions. Hypergeometric functions. Okay. In this case, given a function f, okay, given a function f, and the arguments are a, b, c, z. Okay, so this is defined as in integral form. This is defined as c gamma of c by gamma of b into gamma of c minus b, integral from 0 to 1 t to the power b minus 1 and 1 minus t to the power c minus b minus 1 and 1 minus t z to the power minus a dt. Okay, and we'll be using a specific form of the hypergeometric function in our problems. What we call as the integral representation of Gauss hyper geometric function. Okay. So in this case, we denote a function, say f of a, b, c, z is equal to 2 gamma of c divided by gamma of b into gamma of c minus b, an integral from 0 to pi by 2, and then sine 2 to the power b minus, this is 2b minus 1, and then cosine to the power 2c minus 2b minus 1t, and then dt divided by 1 minus z sine squared t to the power a. Okay, this is what we'll be using in our, we will be using this in some of our problems. And it won't be so tough to move from this, this form to the other form. It just needs that we need to put, we need to substitute, say some, say s is equal to sine squared t, and then we'll, after performing some manipulations, we can arrive at our, and we'll try to do this in one of our problems. Okay. And for nanomechanics, I'll just be reviewing one particular concept. Just the what we call as the interaction energy, right? So I'll just be reviewing one particular thing, which is interaction energy. Interaction energy. This comes in. It is the energy between, say, for two separate non-bonded molecular structures. And let's use both the forms. One is what we call as the discrete, in discrete framework. In discrete framework, or when we have all the atomic pairs, right? Then in this case, what we have is that I'll just denote interaction energy as IE. Then IE per atomic pair is given as a phi of rho ij, where rho ij is the distance between I between atom pairs I comma j, right? And the total interaction energy for all the system, for all the atoms in a system, then we'll have E is equal to double summation ij and then phi of rho ij. So essentially, we just sum up all the interaction energies per unit, per atomic pairs. Then what the next framework is our continuum framework. When we have a large number of atoms in a system, then we cannot uh, actually go pairwise. What we have to do is we have to then this discrete system tends to be a continuum in a limit, isn't it? As limit of particles tend to infinity, then the discrete framework becomes as if it were a continuous framework. Okay, as if it were continuum, which means we have infinite atoms in that in the system that we are trying to study. So in this case, what we'll assume is we'll assume that atoms are uniformly distributed over the entire range of surface. Okay. Then in this case, what will have happen is then we will this limit of this the double summation, this particular thing, it tends to be converted into an integral. So what we'll have is total I is given by total I of a system is given as E is equal to eta 1 eta 2 integral over the surface S2 S1 phi of rho dA1 and dA2. Now eta I, this is the mean surface density of atoms of ith molecule surface Si. Fine, isn't it? So this is what we'll be using. So this tends to just integrate over the say infinitesimal atomic element, if I call that. I also not use that. It's more of a, you have a small element or a small volume of the mass surface that we are trying, whose interactions we are trying to compute, and then we just do it in, we just integrate over the interactions over both the surfaces. Okay, and dA1 and dA2 are they are just the infinitesimal surface area of both the system of both the surfaces. Now what you have is, before we move on, let me also define what we call as the Lennard-Jones potential, also known as, also we'll call it as LJ potential. And here what we'll have is we'll have phi of rho is equal to minus a rho, rho to the power minus m plus b, also can be a function of rho to power minus m. And rho is, as usual, distance between two atoms. Okay, and this minus a component, or this part, is what we call as the attractive component. And this part is our repulsive component. One thing to notice here is that the attractive component has a sign of negative and the repulsive component has a sign of positive. And this you'll find in the way we define our potential, right? That the attractive potential is always denoted with minus. Even if you consider the gravitational potential, it will also be negative, isn't it? And because gravity is always attractive in nature, that's what makes that the gravitational potential is always positive, always negative. And when we call about when we talk about the repulsive component, that is always positive nature, and this can happen in electrostatic systems as well as magnetostatic systems where we have both sorts of components. It can be some reasons can have, or some electric discharges can have positive, can have attraction. Some other pairs can have repulsion. So effectively we just add both the pairs. That's what we try to claim here. Now usually m and n, they are natural numbers, or the set of positive integers. Okay. And in most of our in all the common cases, we have m is equal to 6 and n is equal to 12. Right? This is what we typically take for many systems, or for many electron systems, to define our Lennard-James potential. Sorry, it's James, not Jones. Sorry. Okay. So I think we have covered necessary ingredients that we are going to need to solve the problems in this tutorial session. So we just went through gamma function, and then discussed few properties. We also talked about hypergeometric functions, and the special integral representation of Gauss hypergeometric functions, and then talked a bit about nanomechanics, just the interaction energies in both discrete and continuum framework. And furthermore, we talked about Lennard-James potential. Right? Now I think is a good time to start solving our problems, solving some solving some problems for this tutorial session. Okay, so let me start with a problem. The first problem is that a spheroidal surface P is given parametrically by the position vector r theta of phi as r theta phi is equal to b cosine theta sin phi b sin theta sin phi, comma b cos phi, where minus pi is in theta is phi and 0 is less than phi, and the constant b is the minor semi-axis length is the measure, and p is the minor semi-axis length. Now we need to determine the surface area. S is equal to double integral of P, where as a this should be as a function of B and C. Okay, B and C, where B and C are related through epsilon square is equal to 1 minus c square by b square. And epsilon, you know very well, it's called the eccentricity of the ellipse, or one if you cut through the largest section of the spheroid, then it will result it as ellipse, right? So it's the ellipse is the elliptic it is the eccentricity of that elliptical cross section. Okay, now let's solve this problem. And at first let's talk about, or at first let me tell you, how do you define the area surface, isn't it? So the general formula, and this can be obtained, um, or you can understand how to obtain this expression from differential geometry. It essentially comes from there. The general surface expression for or to determine the surface area of a parametrized surface, or of a surface parametrized by, say, theta and phi, as, or this is the general to determine is S is equal to double integral of the norm of partial r partial theta cross partial r by partial phi d theta d phi. And remember that r here are vectors. This and these are r as vectors. So that's how we, and even if you see our parametrization here, this is actually our Poisson vector, isn't it? And the limits of theta is from minus pi to pi, and for phi it is 0 to pi. Okay, so our task is essentially to determine the components which are required to solve this expression. So let's first start with partial r vector by partial theta. And this you know very well is we'll differentiate component by component with respect to theta. So the first component is minus b sine theta sine phi, and the second component is b cosine theta cosine it's sine phi. Just for your information, let's just copy this term so that it's right in front of our eyes, right? So just keep it here. Okay. And the third term is c cos phi. So with respect to theta, it is 0. And this, now let's partially differentiate our r vector with respect to phi. And this gives us the first component is b cosine theta cosine phi. Second component gives us b sine theta, and this is also cosine phi. Okay. And the third component is minus c sine phi. Okay. With this, now let's determine the cross product of these terms. Partial r vector, partial theta, cross partial r vector by partial phi is equal to, let's use our this approach. So minus b sine theta sine phi, and then b cosine theta, sine phi 0, b cosine theta, b sin cos phi. Then we have b sin theta, cos phi, and then minus c sin phi. Okay. Okay. Now let's take over the now let's so for the component I vector, it is minus b cos theta sin square phi, and then the other will be minus of 0 into the term, so it just equals to 0. So the second is j vector. For this we have 0 into b cosine theta cos phi, so it's 0. Then minus into minus b into minus of this term and this term, right? So we have is 0 minus b b. Prior to this, it was I'm sure it should be bc. Okay, so it's minus bc, and then we have sine theta and sine square phi. Now for the kth component, we have minus of b squared sine square theta sine phi cos phi minus of b square cosine square theta sine phi cos phi. Okay, and this we can reduce it to, say, I'll just call it as minus of bc cosine theta sine square phi I cap minus of bc sine theta sine square phi j cap and plus. And in this case, what you see is for the kth component that you can have b square sine phi cos phi as the common factor, and then and within the brackets you have sine square plus cos square theta, so it evaluates to 1. So that's why our result is minus k cap for rather minus b squared sine phi cosine phi sine phi cosine phi to k hat. Okay. Now let's uh, take the norm. Partial r vector by partial theta cross partial r vector by partial phi. The norm is square root of the first term is bc cos theta sine square phi minus of bc squared, then plus minus bc sine theta and the sine square phi whole squared. And then the third is plus minus b squared sine square, so sine theta, sorry, sine phi and cosine phi whole square, right? Yeah. Now what you do is from the first two terms, what we see is after squaring it, you'll have b square c square into sine to the power 4 phi, and then that will be common factor, or not common, yeah, that is common to both the first and second term. So what we can do is let's have something of this sort: b square c square, and then sine to the power 4 phi, and this will have cosine square theta plus sine square theta. And for the second time, we'll have b to the power 4 sine square phi, and it evaluates to cosine square phi, right? So I'll just use the trigonometric relations to have just my 1 minus sine square. Now this gives us b squared c square sine 4 phi plus b square sine square phi minus b to the power 4 sine to the power phi. Now, from the eccentricity definition, epsilon square is equal to 1 minus c squared by b square. What we can have is c square by b square is equal to 1 minus epsilon square. And then this gives us c square is equal to b square minus epsilon square. So effectively, this here becomes, let's substitute the expression for b, for c in terms of b squared. So we'll have b to the power 4 and 1 minus epsilon squared into sine to the power 4 phi plus b to the power 4 sine square phi minus b4 sine to the power 4 phi. And eventually what we have is, we have certain terms cancelling out, right? So what we have is minus b4 epsilon squared sine to the power 4 phi plus b4 sine square phi. And this we can simply, this implies that partial r vector by partial theta cross partial r by partial phi, the norm of this becomes, we will take out the expression of b square and sine phi. So v square sine phi into root over 1 minus epsilon square sine square phi. Okay, so now we are on our so now we can so this implies that therefore the infinitesimal infinite area element is dA is equal to b square sine square, not sine square, it's just sine, right? It's some, yes, just sine 1 minus epsilon square sine square phi d theta and d phi. So these are infinitesimal area. Now the total area is what we are going to determine, right? The question asked us to determine the surface area. The surface area S is equal to double integral of dA, isn't it? And this comes out to be, then this implies that S is equal to, the limits for theta is minus pi to pi, that for phi is 0 to pi, then b squared sine phi root over 1 minus epsilon squared sine square phi d theta d phi. Now what you see is the integrand is, this is our integrand. And you can clearly see that integrand has no dependence on theta, isn't it? Because b is a constant and even epsilon is a constant. So which means that we can just what you call just separate both the integrals in a sense. We'll have b square common and then minus pi to pi d theta 0 to pi. So it's a product of integrals. 1 minus epsilon square phi d phi. And then this first term evaluates to, this implies that S is equal to d theta is just theta, so minus pi to, so it's 2 pi. So we'll have 2 pi b squared 0 to pi sine phi root over 1 minus epsilon square sine square phi d phi. Now let's utilize some of the properties of pi here. Now, when you look clearly at that all the integrand contains terms just in sine phi, and you know very well that of a range of 0 to pi. Now, if I draw uh, 0 to pi, right? Let this be our phi axis, and this is our sine phi axis. So what you see is the graph goes like that. It reaches a maximum of pi by 2 at pi by 2, and then it falls down to 0 again. Maximum of 1 at pi by 2. What you see is about this line, this as well as these are this the sine graph or the sine curve is, or yeah, the sine graph is symmetric about pi by 2. Is it not? And you can verify this very well from our trigonometric identity sine pi minus x is equal to sine x, right? So it denotes some sort of a this is a symmetry relation. So what you do is in this integral of ours, 0 to pi is the same as 2 into 0 to pi by 2, isn't it? So we just use that symmetricity property is equal to 2 into 0 to pi by 2 sine phi root over 1 minus epsilon square sine square phi d phi. And so on the next slide, let me just write it down as this implies that S is equal to 4 pi. Now what I'll do is I'll just replace B by capital B. Now you'll ask, why am I doing this? The thing is, since we are required to determine the surface area as a function of B by C, and we will use our we'll express it in terms of a hypergeometric function. So, and then you know that one of the argument of the hypergeometric function is B. So just to avoid conflict with that term, I'll just write it as S is equal to 4 pi capital B squared. Okay. And then 0 to pi by 2 sine phi root over 1 minus epsilon square sine square phi. Is it not? And then d phi. Now let's use two approaches to solve this, to express this in terms of this component in terms of some trigonometric identity, right? Oh, sorry, in terms of we need to express this as a hypergeometric to remove to eliminate conflict with hypergeometric function. Okay, so from the identity that I had discussed from the integral representation, right? I'll use two methods. One is from the integral representation of Gauss hyperbolic function. I'll just call it as HF, isn't it? So Gauss HF, and the standard we have that A f of A, B, C, and Z is equal to 2 gamma of C divided by gamma of B, gamma of C minus B, and 0 to pi by 2. Is it not? And then we have sine of 2B minus 1T and cosine 2C minus 2B minus 1 of T and then divide by 1 minus z sine squared t power minus to the power a and dt. Now let's compare. Upon comparing what we have, this implies that upon comparing upon comparing what do we have? The first thing that we have is that t corresponds to phi. The next other things are now relevant. This was just our dummy variable, so it doesn't matter much, but still it corresponds to this one. And now when you take a clear look at, now let's what you call match the terms. Now this term here is very is close similar to this, right? So here it is sine phi, and here it is sine raised to the power 2b minus 1 into t. So what can we say from by comparing this? We can have that 2b minus 1 is equal to 1. Okay. And then we see that in this integrand there is no cosine term, but we have here as a cosine term outside of that square root. So what we have is we'll have to match its power to, I'll just write it down here. So 2c minus 2b minus 1 is equal to 0. And when you take a look at the term of the square root, now this is just square root. Okay, so it's like 1 minus epsilon squared sine square phi to the power half. And here you have 1 minus z sine square t to the power a. And if we bring it as a numerator, then this term will have exponent of minus a, right? So what I'm trying to say is that a is equal to minus half. And also that this is the square root term here, since sine square phi is the same as sine square t, so we'll have as z is equal to epsilon squared. Is it now? Okay, so let's go on to solve the 2b minus 1 is equal to 1 gives us 2b is equal to 2, and then b is equal to 1. Likewise here what you have is 2c minus 2 minus 1 is equal to 0. So this means that 2c is equal to 3 and c is equal to 3 by 2, right? Okay, so our hypergeometric function is, let me first substitute all the terms here, and let me just remove this part and then erase this part, and then we'll have z is equal to epsilon square. And then so what we have here is that that 0 to pi by 2 of sine phi root over 1 minus epsilon square sine square phi is equal to, so we were just matching this term and this term, right? So which means we need to, so to equate this, we'll have f of abcz divided by 2 into gamma of c divided by gamma of b gamma of c minus b, right? And this I can write it down as gamma of b, which is 1, and then gamma of c minus b, which is 3 by 2 minus 1 divided by 2 into gamma of 3 by 2. And f of a is minus half, b is 1, c is 3 by 2, and z is epsilon squared. Okay, so our total surface area S is equal to 4 pi capital B squared and into gamma of 1 and gamma of half by gamma of 3 by 2 into gamma of 3 by 2, and f of minus half 1 and 3 by 2 epsilon squared. And what you see here is this cancels out to give us 2 pi b squared gamma of 1 gamma of half by gamma of 3 by 2 into f of minus half 1 3/2 epsilon square. Now let's use our gamma properties. We know that gamma of 1 is equal to 1. Fine. Now we also know that gamma of x plus 1 is equal to x of gamma x, right? So here when we have, then this implies that gamma of 3/2 is equal to f of half plus 1. So this means that we have half of gamma of half. So upon substituting this, we have s is equal to, I'll write just or 2 pi capital B squared gamma of 1 is gamma of 1 is gamma, who is 1, and then gamma of half by gamma of 3/2 is nothing but half into gamma of 1/2 into f of the rest. So this cancels out. So therefore, s is equal to 4 pi b square to f of minus half 1 3/2 and epsilon squared. And this is, and here b is the semi major axis, okay, length. And it's the same as small b of the question. Okay. Now let's use the other that we thought of. We'll also use the other method, right? This was the direct approach, and now we would like to convert it into copy. Okay, let me copy it again. Let's try. Now let's use the standard, the other form that we have, isn't it? So we need to evaluate this in terms of our trigonometric, in terms of the original hypergeometric function, which was in terms of t, right? So let's evaluate. Let's start evaluating in that sense. These are second approach, which is going to be cumbersome, but still let's do it. These are integral, which is s is equal to 4 pi b square, right? Okay. First approach 1. These are approach 2. Okay, so let's evaluate this function, this integral. So let's take t is equal to sine square phi. Okay. So then this implies that dt is equal to 2 sine phi cosine of phi into d phi. Is it not? And now what you see clearly from here is that this implies that sine of phi d phi is equal to dt by is equal to dt by 2 cosine phi. Is it not? You see, right? We are just rearranging this term. And mind you that this implies that sine phi d phi is equal to dt by 2 into cosine t, And then you'll when take a look at clearly that the cosine t is why don't I expand it right here, right away here? So this is dt by 2 into root over cosine square phi, and then this will be as dt by 2 into root over 1 minus sine square phi. Is it not? Yes, right? So this means that we have dt by 2 root over 1 minus t. Okay. Now, and then at phi is equal to 0, t is equal to 0, p is equal to pi by 2, t is equal to 1. So our integral eventually becomes, this integral I'll call it as say a. A is equal to 0 to 1. And mind you that I had used this sine phi d phi just because I have sine phi and d phi. So before that, let me just express this as 1 minus epsilon squared t, and then the others as dt by 2 into 1 minus t. Okay. And this implies that this is equal to, let's take out 2, and then we have 0 to 1. Is it not? And then for the rest, what we have is 1 minus t to the power minus half, and then 1 minus epsilon squared t to the power, just a minute. Okay, yeah, it's fine. To the power half of dt. Okay, now let's compare with, before that, let me also write what you call s is equal to, then it becomes 2 cancels, so it becomes 2b pi b squared, 0 to 1, 1 minus t to the power half. Why don't I take it? Oh, I'll just take it to the next page. Okay, so let's compare with the standard form that we have is compare with we need to compare this with f of a b c, z is equal to, and what was the why don't I just copy from here? Copy, and then move this, paste. No worry, even if it, just drag it. No. Okay. Now what we do is let's compare the integrals. Okay. Now what you say is comparing what you have is, this implies that first of all, we have 1 minus t here as well as here. So we can compare the powers. So the power is c minus b minus t is equal to minus half. Fine. And the second thing we need to do is For the other term, what we have is this. And here 1 minus t z, and here we have 1 minus epsilon square t. So this means that z is equal to epsilon square. So this is done resolved. And then we can also have the power. So minus a is equal to half. And the third thing is we don't have a term just containing t, right? In our original integrand. So what we'll have is we'll equate the power of t b, which is b minus 1 to 0. So this means that b is equal to 1, a is equal to minus half, and this we have as c minus 1 is equal to minus half. And this gives us c is equal to 2 minus half is 3 by 2, right? So effectively, um, our integral, I'll call it as c here. So c is equal to f of a is minus half, b is 1, c is 3 by 2, and z is epsilon squared divided by gamma of c, which is 3 by 2, and then gamma of b is 1, and gamma of c, this is nothing but half. And this we recall very well here that from our that this term here is let's just write it as that gamma of 1 is 1 into gamma of half is half, gamma of half is gamma of half, and then the other one is half into gamma of 1 by 2 into f and the rest of the arguments. So this cancels out to have 2f, right? So therefore s is equal to 4 pi b squared and f of minus half 1 3 by 2 and epsilon squared. Okay, and that mind you that b is nothing but actual b of this spheroid. And you see that the results are the same, 4 by b square, and we have also the 4 by b square, isn't it? Okay. Okay, now let's solve this next question. So the next question is that consider an atom located at P, which is 0, 0, del on the z-axis, and a circular ring molecule lying in the xy plane, centered at the origin with radius r, and with uniform atomic line density eta. Use the Leonard Jones. Okay, I think I was right. It should be Leonard Jones. Potential to mark the to obtain the total van der Waals interaction between the atom at P and the ring molecule. Okay. So let's begin to solve this problem. So the solution goes as we have a circular ring placed in XY plane, right? And the center at origin, X, Y, and the radius is R. And we have a atom located at P, which is 0, 0, del. Okay. And any point on this is X, Y coordinate on the circular ring molecule. Okay. So our charge density is, or the atomic uniform atomic land density is, N is the uniform atomic line density. Okay. And now before that, let's determine the distance. So the distance between particle lying, or I'll just call it distance between an atom. That's a more apt word. Distance between an atom lying on lying in the circular ring molecule and point P, and the atom at point P is, I'll just let's call it as rho. So rho squared is equal to 0 minus x whole square plus 0 minus y whole square plus del minus 0 whole square, right? It's ideally is xy 0. So this means that rho square is equal to x square plus y square plus del square. And we know very clearly from our that this x square plus y square, this actually lies on a circle, and which is given by x square plus y square is equal to r squared, isn't it? So then this means that we have r square plus, and you saw that both r and del are constants, isn't it? Okay, so now what we do is we'll find the total interaction energy, right? Or total interaction or total van der Waals interaction energy. And this is very well given by E is equal to, and the linear density is S eta. And what we need to do is we have to actually integrate over every small infinitesimal element on this circle. And so then this is phi, and let me just denote this circle to be C. So integrate over C, and we have phi of rho and eta d of s, and ds is an infinitesimal length or arc length element on the ring, on the circumference of the ring. of the. So what we have is we need to take for rho of phi. This will from this from LJ or Leonard Jones potential. Is it not? So we'll have phi of rho is equal to minus a, and we'll take all the other constants. So we'll have a constant, and then the other is rho to the power minus 6 plus b rho to the power minus 12, isn't it? So we'll substitute this in our expression here. So E is equal to eta T. Before that, let me write our minus a rho to the power minus 6, and this can also be written a by rho square to the power cubed plus b rho square to the power 6. So we'll just use that notation here, and all we have is a by r square plus del square to the power cubed plus b by r square plus del square to the power 6 into, and now mind you that now we can start, we can parameterize the element, the any point on this, on the circumference of the circle as in terms of theta, and then this theta is the angle with respect to x-axis. So this point we'll call as r cos theta, r sin theta, is it not? And we'll see that ds is from our from what we learned during high school in our high school is that the angle subtended by a small element, this one, right? An arc is, and in this case, what we are trying to say is by segment ds. So ds segment by r is equal to d theta, isn't it? Because ds subtends an angle of d theta at the origin. So this means that ds is equal to r d theta. And then theta goes from 0 to 2 pi, is it not? So, and I'll just call it as r d theta, and theta goes from 0 to 2 pi. Now what you see here is every term in this case happens to be a constant, right? A is constant, R is constant, del is constant, and B is also constant. So what we can take, what we can have is, we'll just have eta R and the entire term of minus A divided by something plus B by divided by something into integral of 0 to 2 pi d theta. So which means the total van der Waals interaction energy is E is equal to 2 pi eta R, and then we'll have minus A by the same thing to the power cube plus B by square plus del square to the power 6. So there is our interaction energy that we are trying to compute. Okay. Now let's move on to a third question. Okay. And here the question says that the question says that the question says that consider calculating the Leonard James potential, or ES, a potential James interaction energy, sorry, interaction energy ES of a spherical surface S with radius A and atomic density eta s with some point, a distance away, a distance delta, provided the delta is greater than a, from the center of the sphere, assuming the continuum approximation and the Leonard zones constants A and B. Now, say after adopting a certain an appropriate parametrization, obtain the expression for the interaction energy Yes. Okay, so this is a quite long question. So let's read it. It says that consider calculating the Leonard John James. I say Leonard Jones. I keep on Leonard James interaction energy ES of a spherical surface S with radius A and atomic density eta S with some point a distance del away, and where del is greater than the radius of the sphere from the center of the sphere. Now, assuming the continuum approximation and Lena zones constants A and B, and after adopting appropriate parameterization, so after adopting the appropriate transaction or the appropriate parameterization, obtain the expression for the interaction energy, which is given by ES, isn't it? So let's start working on this. Okay. Okay. So let's assume some suitable parameterization, right? Now, what we do is let's have a orientation in such manner that let's set up our coordinate system x, y, z, and we have a sphere whose center is at origin. I don't think whether there is really a sphere. Now let me draw a better one. Okay, so these are sphere with radius at origin, and with the center at origin, and this is of radius a, and let's set up our coordinate parameterization such that consider a point P, and point P, so the Poisson vector of point P makes an angle of P with respect to z axis, and then the projection on the xy plane makes an angle of theta, and such that we have theta goes from 0 to 2 pi, I call that, or you can even have minus pi to pi. We'll stick with 0 to 2 pi in this case. Or either are equivalent, if I call that. And then phi goes from 0 to phi, 0 to pi. And let's take the point at which was supposed to be a distance del from the center of the sphere on the z-axis for the case, for the very simple thing of due to just for a convenience. Okay, and you see that, yeah, it is at a distance of del from the center of the sphere. Okay, so the parametrization of any point of the surface of the spherical surface S is that r vector of is a function of theta, and phi is given by a cosine a sine phi cos theta, a sine phi sine theta, and a cosine phi. Okay. Now before that, let's also find the distance, and let's call it as q, the point at 0, 0 del. So the distance between P and Q is, we call it as rho square is equal to uh, uh, I'll just call it from 0 minus a sine phi cosine theta square plus 0 minus a sine phi sine theta square plus del minus a cosine phi squared. Is it not? Now let's take it to the next slide. Rho square is equal to a square sine square phi cosine square theta plus similarly a square sine square phi sine square theta plus what you see is del minus a cos phi squared. And this we can write as now in this, for the first two terms, you say that a square sine square phi uh, is a is a common factor, right? And so, and then cosine square theta plus sine square theta is 1. So then plus del square minus 2a del cosine phi plus a square sine square a square cosine square phi. And what you see is we can even reduce the first and the last term. This gives us, then we'll have just del square plus a squared minus 2a del and cosine phi. And using our trigonometric identity, we can write del square a square minus 2a del, and this we can write as 1 minus 2 sine square phi by 2, is it not? And this gives us del square plus a square minus 2a del plus 4a del sine square phi by 2. And we can write down in a neat form as del minus a whole square plus 4a del sine square phi by 2. Fine. Okay. Now let's write the expression for the interaction energy. It's given as ES is equal to, and we were given a surface atomic density as eta s. So eta of s, an integration over the surface This is a double integral over the surface S, and ideally this should have been, this our S, or S is this. Okay, surface S is, and then we have from the Leonard zones, we have minus A by rho 6 plus B by rho to the power 12 into what? Into our dA, is it not? Now I'll ask, fine, but what about dA? Okay, so for that, let's go back to our first question. There lies our answer. For the first, it was said that this was a spheroid, which means it's not a sphere, but it was some sort of a distorted sphere, or what to be more accurate, we call it an ellipsoid. So here C and B, C and B, C and B are the minor and major axis, major and minor axis respectively. And there is epsilon square which relates both of them. Now what you say is for our sphere, both B and C are equal, is it not? Yeah, it is. The minor and major axes are the same thing for a sphere, or otherwise it's just where for a sphere we just have one dimension which one parameter which defines the sphere, is it not? Defines all we need is a radius, isn't it, and a center. Okay, that's fine. But yeah, so here C is equal to B, so which means that in this case even epsilon square is equal to 0. Okay, and then when we had derived an infinitesimal area element, what we had is, this was our expression, is it not? Now let's take a look at the expression clearly. So here we have B square, and for our case B was, A was the radius of the sphere, right? So it's this A square sine phi and root over 1 minus epsilon squared sine square phi. Now you must know that epsilon for a sphere is 0. There is no eccentricity. So you have B squared sine square phi, because then you have, sorry, B square sine phi, and the term is within the square root evaluates to 1. So it's just B square sine phi into d phi, d theta d phi. I'll just note it down here, where dA is equal to A square sine phi d theta d phi. Is it not? Okay, so now let's evaluate it to E of S is equal to eta of S. And now let's put in all the limits that we need right now. So for theta, our limits are minus 0 to 2 pi as we have chosen. For phi, it is minus 0 to phi, 0 to pi, and then we'll have minus a by. Now you must note that rho here, I'll just call it as rho. Rho here is both del and a are pure functions. They are constants. So it means rho is a function of phi. So I'll just denote as rho as a function of phi to the power 6 plus b rho to the power phi as a function of phi. And then we'll have as a squared sine phi d theta d phi. Now let's take a look at the integrand, which is this our integrand. You see that is there any dependence on theta? No, is it no? So it means we can separate this double integral in terms of a product of integrals. So all that we'll have is theta s and a square comes out. So 0 to 2 pi into d theta and 0 to pi and the rest of the terms sine square phi d phi. So this implies that E of s is equal to 2 pi a square eta of s and 0 to pi, and what we'll do is minus a by, we had a large expression, is it not? Del minus a whole square plus 4a del sine square phi by 2. and this was raised to the power 3. Likewise, for b, we'll have b by del minus a whole square plus 4a del sine square phi by 2 to the power 6 into sine phi d phi. Now we have a very complex expression. Now what we do is let's separate it in terms of two integrals. So we'll have 2 pi a square eta of s minus of, and then let's do some trick. We'll take out lambda del minus a squared out of this denominator. So we'll have del minus a to the power 6 0 to pi. Is it not? And then sine phi d phi by, and mind you, okay, let's do somewhat. Okay, let it be followed like this. Okay, and then we'll have 1 plus 4a delta sine square phi by 2 divided by, let's do it otherwise. It's 4a delta del minus a whole squared sine square phi by 2 to the power 3 plus b by, we'll carry out a similar operation, del minus a to the power 12 0 to pi, and then you have sine phi d phi divided by 4a delta sine square phi by 2 to the power. So this expression, let's call it as 1. This has 2. We need to evaluate these two integrals. Okay. And what our aim is to evaluate 1 and 2 as hypergeometric functions. Okay, let's pick up the first integral. This one is equal to 0 to pi sine phi d phi divided by what? 1 plus 4a del minus a whole squared sine square phi by 2. Okay, let's make some substitutions. Take t is equal to what? Pi by 2. This is what we wanted. This means that d theta dt is equal to d phi by 2, right? Or likewise d phi is equal to 2 dt. And then at t is equal to 0, no, at phi is equal to 0, t is equal to 0, phi is equal to pi, t is equal to pi by 2. So it means I becomes 0 to pi by 2. And then you have, this I was supposed to write as 0 to pi 2 into sine pi by 2 cos pi by 2 divided by, and this was supposed to be 3, right? 1 plus 4a delta del minus a whole square sine square pi by 2 to the power 3. So we have 0 to pi by 2. This was with the pi. So this we have 2 into sin t cos t, and dot 2 into dt divided by 1 plus 4a delta del minus a whole square. Again, for our simplicity, right? Let's just call our a as capital A del, and you'll know why. Pi cubed. Okay, so this means evaluates to 4, and essentially it's just 4. So why don't I just take this 4 out? Now you compare with f of a, b, c, z. Now here a is equal to a, right? This was supposed to be 0 to pi by 2. Not before that, we have 2 into gamma c, gamma of b, gamma c minus b, 0 to pi by 2, sine to the power b minus 1, right? Was it? Yeah, to 2b minus 1 into t, cosine 2c minus 2b minus 1 into t, and dt divided by one minus z times 20 power a. Okay. It was supposed to be 2b, 2c. Okay. Now let's compare. And comparing gives us at the first place you have what do you have here is that we need to have 2b at the first. Yeah, let's start with sine. So 2b minus 1 is equal to 1, and 2c minus 2b minus 1 is equal to 1, and z is equal to minus 4 capital A del minus by del minus a whole square. And the fourth thing was a is equal to 3. This means b is equal to 1 plus 1 is 2. So 2b is equal to 2 is b is equal to 1. And then this we have 2c minus 2 minus 1 minus 3. So this means that 2c is equal to 4. So c is equal to 2, right? And then also now using this, let's evaluate 2 gamma c is equal to 2 gamma c by 2 gamma b. I'll write it on as 2 gamma c is 2, and gamma 1, and gamma 2 minus 1 is 1, right? So you'll have 2 into 1 into gamma of 1 divided by gamma 1 is 1. So all that we have is 2. Is it not? So which means that this expression here, this expression here becomes f divided by all the rest of the terms, and the term just gives us 2. And so what we'll have is this is equal to 4 into f by f of 3, 2, 1 minus 4, and I'll replace again a by del minus a whole square by 2. So this one just comes to be 2. Okay. Likewise, integral 2 evaluates to, all that changes is the value of a. So integral 2 evaluates to 2 into f, and this you can verify, please. A is 6, 2, 1, and minus 4a del by del minus a whole square. Okay. Okay. Now let's put it back in our original expression. So we'll have ES is equal to sorry, I think I have made some mistake here. No, it's all right. So 2 pi a square theta s to minus of a by del minus a to the power 6 into 2f 3 to 1 minus 4a del by del minus a whole square plus b by del minus a to the power 12 dot 2f 6 to 1 this is our expression that we need to find. So yeah, so I think with this I have reached whatever I had to teach in this tutorial session. I hope I was able to convey the ideas that were discussed in week 11 of this course. And I think we'll close today's tutorial session, and let's discuss. You'll find the presentations hosted in the link that I provide, and in the next two sessions, we will be reviewing whatever has been covered in the entire course and discussing some of the questions in week 12 of the course. Because since week 12 won't have any lecture videos, so all that we'll be doing is reviewing the first half, if possible, of this course, and in the last lecture, in the last tutorial, we'll be covering the second half of the course. Okay. So yeah, so let's close today's tutorial session. Let's meet again on 18th April, where we'll be reviewing whatever has been discussed throughout the entire course. Okay. Bye.